Hello and welcome to another geometry lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 2, Lesson 2 on rotations, Day 1. Not surprisingly, the next lesson will be Day 2. So we're going to be talking about, all throughout this unit, geometric transformations. And today we'll start to look at one of the most important ones, which is that of a rotation. I do have a little scientific calculator handy, because I want to make sure that we can use that if we've got some numerical work to do. You might want to have one handy as well. So let's begin by talking about something that we mentioned in the last lesson, which are rigid motions. Now there's many types of transformations that map points in the plane to other points in the plane. But a very important type of transformation is that of a rigid motion. And let's talk about what is true about rigid motions. Rigid motions are transformations that have three specific characteristics. They map lines to lines, rays to rays, and segments to segments. They preserve the distances between two mapped points, and they preserve angle measurements between two mapped rays or lines or segments or whatever. Now again, let's talk about each one of these things. The first one almost seems like a toss-in, but it's actually quite important. There's many geometric transformations that might take a line and map it actually into a curve or something like that. Rigid motions will take a line segment, and when you map it, it will continue to be a line segment. It won't change into a circle or something like that, okay? So that's very important. But the other two things are the real keys about rigid motions, right? One of them is that they preserve distances or lengths. So if I take a line segment and I map it with a rigid motion, its image will have exactly the same length as the original segment. And the second piece, they preserve angle measures. That's important because that means that the shape of an object won't change. In other words, if I take an angle that's 45 degrees and I map it using a rigid motion, the image angle that I get will also be 45 degrees in measure. Okay, let's take a look at exercise number 1. Triangle ABC is graphed below with vertices at A, -2, 3, B, -2, 7, C, 4, 3. A geometric transformation is given below. F of x, y goes to y, -x. I feel like we've seen this one before. Letter A, show how each vertex is mapped using this transformation. Then plot and label the points. Draw triangle A', B', C'. Okay, well let's review this a little bit. Remember, what I'm doing is I'm taking a point x, y, and my new x coordinate was my old y coordinate, and my new y coordinate was my old x coordinate, whose sign has now changed. So, if I take A, which is at -2, 3, where will it go? Well, my new y coordinate, or my new x coordinate is my old y coordinate, and my new y coordinate is the old x coordinate whose sign has changed. So A' is now 3, +2. What I'd like you to do now is I'd like you to run both B and C through the same transformation to get points B' and C'. All right, let's do it. So point B, which is at -2, 7, will become point B', 7, +2. And C, which is at 4, 3, will go to C', which is 3, -4. Now let's draw this. A' is at 3, 2. B' is at 7, 2. And C' is at 3, -4. I'm just going to hand sketch this in to save us a little bit of time. All right, so we have triangle A', B', C' compared to triangle ABC. All right, letter B. Is this transformation a rigid motion? Use tracing paper to verify. All right, so what I'd like you to do is take tracing paper, trace out triangle ABC on the tracing paper, and then see if you can lie it on top of triangle A prime, B prime, C prime so that they completely coincide. Go ahead and take a moment to do that. Now, when you do that with tracing paper, obviously after you've traced out the triangle, which I've got right here, okay, once you've done that, you're going to have to move it around. You might have to flip the tracing paper over, you might have to rotate the tracing paper, etc. So, you know, I bring this thing down. Maybe I have to rotate it some. Let's see. Look at that. Yep, right on top. Right, even on top of my horribly traced out triangle, right? So the answer is yes. Right? Definitely lies directly on top. Okay, so this was a rigid motion. Now, final little piece, letter C. Using a compass, draw arcs centered at the origin that connect each pre-image point with its image point. What do you notice about the arcs? All right, so this is kind of cool, and it really gets into what we're doing today. If I take my compass out, and let's say I rotate it so that it is, really delicate. There we go. Pretty good, actually. Right, it's going through point A, and I draw an arc. Notice that goes through point A prime. And now if I make it so that it goes through point B, that also goes through point B prime. And finally, let me get it so that it goes through point C, probably easier for you than me. Come on. Well, I can't quite get it to go exactly through point C, but there it goes. Right? So this is kind of cool. And you know, what are we trying to really see here? Well, one thing that we're seeing is that each one of these points, right, is on a circle with its image point where the circle is centered at the origin. Now, a little bit harder to see is that each one of these arcs is actually a quarter of a circle. That might be easiest to see with point B, right? Because point B is sort of at the top of the circle. Well, actually, it's not at the top of the circle, but it's here, and then it comes down here. So each one of the image points, whoops, each image point lies on a quarter circle centered at the origin with its pre-image point. All right. And really the most important thing isn't it about being a quarter circle. The most important thing is that each one of these points, each image point, lies on the same circle as its pre-image point, a circle that in this case is centered at the origin. So let's get into what we're really looking at here, right? Which are moving points along a circle, right? Transforming points where we move them along a circle. Let's take a look at exercise number 2. The diagram below shows circle C, which has radius CA. Two image points, A prime and A double prime, are shown with ray CA prime, and ray CA double prime drawn. We want to think about how to transform A by moving it along the circle so that it maps to point A prime or to point A double prime. Assume we will move the point the shortest distance possible. All right, now by the way, this assumption in bold is only for this particular problem, okay? So let me just move this up a little bit, and let's take a look at letter A. Would you map the point, would you map, parentheses, move A to A prime, moving clockwise or counterclockwise along the circle? All right, so in other words, if I'm taking A, all right, and I want to move it along this circle so that it lands at A prime, would I move it clockwise or counterclockwise if I'm going the shortest distance possible? Well, I'll move it clockwise, right? Now it's very important, right? I know that most of the students watching this video mostly read time in terms of, using a digital clock. But a lot of what we're going to do in this particular unit, we're going to talk about clockwise and counterclockwise, right? So the idea is that if I have a hand on a clock, it moves this direction. That's clockwise. So if I'm at A and I want to move that point to A prime in the shortest distance possible, right, then I'm going to move it clockwise. Counterclockwise is literally if you move in the opposite direction that a clock's hands would move in. So in this case, it would be clockwise. The more I say that word, the funnier it sounds. Letter B. What is the measure of angle AC A prime? All right. Well, for this, you obviously have to use a protractor. So let's bring our protractor up and over. And we'll just kind of rotate it down like this. And it looks like that angle is 60 degrees, right? So again, make sure you're reading your protractor correctly, but on our protractor, we're going to be measuring it off on this particular inner scale as opposed to the outer scale, and that is a 60-degree angle. So the measure of angle AC A prime is 60 degrees. All right, letter C. Would you map, parentheses move, A to A double prime by moving clockwise or counterclockwise along the circle? You move that out of there. All right, well, pause the video now and write down clockwise or counterclockwise. All right, well, in this case, right, what I'm doing is I'm taking point A and I'm moving it in this direction. That's very difficult to do. And I'm moving it in this direction, right? And that direction is going to be counterclockwise, okay? Sometimes we'll just abbreviate that CCW. Whoops, and I don't know why that happened, but it did. All right, CCW, counterclockwise. Clockwise is sometimes abbreviated CW. Okay. And again, we can think about what angle we'd have to move it, right? So we would have to move A clockwise 60 degrees to hit A prime, and we'd have to move A counterclockwise by how much for it to hit A double prime? Why don't you go ahead and measure that angle? All right, let's take a look. So we bring this up. Center at C, make sure one of those two rays points at the 0, and it looks like 105, 106, somewhere in there. So the measure of angle ACA double prime, I'm going to call it 105 degrees. That's a nicer angle. Okay, so, right, very, very simple. We can transform points by moving them along circles with particular centers, and we give this a name. It's called a rotation. What we saw in the last exercise is known as a rotation. Rotations are very important types of transformations. They come up all the time in the real world, especially in image editing and things like that. And let's take a look at the technical definition of a rotation. The rotation of point A about or around point C in a specific direction, clockwise or counterclockwise, by a specific angle is accomplished by drawing a circle with a center at C and a radius of CA. The image point is located on the circle such that the measure of angle ACA prime is equal to the specified angle in the specified direction. All right, so it's really convoluted, but the idea is that when we rotate a point, right, we always have to know two things. What point are we rotating it about? That's called the center of the rotation. And by what angle? I'm sorry, we have to know three things. What is the center point? What is the angle? And in what direction are we moving? Are we moving clockwise or are we moving counterclockwise? So if I've got some point A, right, and I've got a center point, sometimes I will be rotating around to hit point A prime clockwise. Sometimes I will be rotating it counterclockwise to reach point A prime. And let's get a little bit of work with that idea in exercise number 3. Circle O, shown below, has points E, F, G, and H marked. Rays are drawn from O through each point, and the angles created by adjacent rays are shown. Answer the following. Letter A. What 2 rotations about point O will map point E onto point G? All right, so in other words, I've got point E, and if I want it somehow to rotate that around point O so that it lands on point G, what are 2 different rotations that will do the job? Well, there'll always be 2 rotations, right? Depending on whether you want to go clockwise or counterclockwise. So let's first talk about going clockwise. If I wanted to rotate point E around this circle so that it landed on point G, right, like that, all right, if I wanted to go clockwise, right, I would have to rotate it through a 95-degree angle and a 54-degree angle, right? And I can really quickly just bring out my simple scientific 95 plus 54. I can rotate it 149 degrees clockwise. So 149 degrees clockwise, okay? But I could also rotate it counterclockwise. All right, let me go in red on that, right? I could take this point and I could rotate it, move it around this circle until it hits point G in that. And of course, that would be then 121 plus 90, which would be 211, I think. 121 plus 90, 211. So I could go 211 degrees counterclockwise. Now, just as a side note, and again, you won't be surprised by this, I'm sure. If I take 149 and I add to it 211, I get 360 degrees, right? And that will always be the case with clockwise and counterclockwise rotations. If I can take a point and rotate it, 100 degrees in one direction, right, then I can take it and rotate it in the other direction, 360 minus 100, or 260 degrees, right? So those 2 angles would always end up adding up to 360, always. All right, let's keep looking at these problems. I'm gonna maybe erase this so that we can make some new markings. Go back to blue, back to blue. Okay, letter B. What 2 rotations about point O will map point G onto point H? All right, so now I want to map point G onto point H. Pause the video now and give me the 2 rotations about point O that will do that. Well, the easiest one is the clockwise rotation, right? So my rotation clockwise, I don't have to do any adding whatsoever. That is going to be a 90-degree rotation clockwise, right? Simple enough. Now, I can also do a counterclockwise rotation. And let me just do this. That will go like that. And I can certainly figure that out by doing 54 plus 95 plus 121, or I could do 360 degrees minus 90 degrees, and I would get a 270 degrees counterclockwise about point O. All right, one final little piece here, letter C. Using a straight edge only, locate the image of point E after a 180-degree rotation about point O. Label it point I. Why does the direction not need to be specified? Okay, so I'd like you to pause the video now and see if you can locate the image of point E, all right, on the circle after a 180-degree rotation about point O. Take a moment to do this. All right, well, 180-degree rotations are kind of unique in the world of rotations because a 180-degree angle, as we know, is a straight angle. And therefore, right, to figure out where point I is, whoops, well, that was kind of cool. Hello. I'm gonna just, and then of course I erased some of this work, counterclockwise. Go back to blue. To figure out where E would land after a 180-degree rotation, we just have to draw a 180-degree angle whose vertex is at the center of the circle. So that is point I. Okay. Now, why does the direction not need to be specified? So there will be times when you're just going to be told, hey, rotate this point about this point by 180 degrees. And they won't say clockwise or counterclockwise. Any other rotation, they've got to give you the direction. But a 180, they won't. And the reason why is, of course, 360 minus 180 is 180. In other words, it doesn't matter because it's a half of a full rotation. Regardless of the direction, you'll end up at the same point. Okay? Because 180 degrees is exactly, hello, red, and still red. That is so awesome. Exactly, exactly 1/2 of a full rotation going clockwise or counterclockwise will result in the same image point. Right? And it's the only one like that. If I say rotate a point by 90 degrees, you have to know whether I'm talking about rotating it 90 this way or rotating it 90 this way, right? But if I've got a point up here and I say rotate it 180 degrees, if I go this way or if I go this way, it doesn't matter. It still ends up down here. And that's pretty critical to understand about rotations. All right. I'm like, I can't even find my, my tool to get me to the next slide. Let's take a look at exercise number 4. In the diagram below, point N is the image of point M after a clockwise rotation about point Q by 125 degrees. Point P is the image of point N after a clockwise rotation about Q by 55 degrees. Letter A. Label the two angles given in the problem on the diagram. In other words, right, that 125 degrees and that 55 degrees show up in this diagram, and I want you to label where they should be at. Pause the video now and go ahead and do that. Now, you might be thinking to yourself, well, there's no circles here, right? That's fine. We don't actually have to have the circle drawn, but to be very clear, right, we are told that point N, right up here, is the image of point M after a clockwise rotation about point Q by 125 degrees. In other words, if we did draw in the circle, it would look something like this, and this angle would be 125 degrees. Okay. Now, we're also told that point P then is the image of point N after a clockwise rotation about point Q again by 55 degrees. So in other words, right, if we just kept on drawing that our circle, that would then be that 55 degree angle. All right, let's take a look at letter B. What three line segments must have the same length or be congruent based on the information in the problem? Explain. All right, we'll pause the video now. 3 of the line segments that are up there in the diagram have to have the same length. And if you've really been following along with what makes a rotation, it should be pretty obvious. Pause the video now. All right, well, the key here is that we're really talking about rotating points, moving them along a circle. Whether that circle is drawn or not is irrelevant, right? But I kind of did draw the circle here, right? Or at least part of the circle. Here, let me kind of draw a really horrible representation of the rest of the circle. This is the center of the circle. All right, and because that's the center of the circle, let me do these in red. Maybe do it a little bit thicker. This is a radius of the circle. This is a radius of the circle, and this is a radius of the circle. These are all radii, right, with this being the center. And as we know, what we reviewed in Unit 1 of this course is that the whole point of a circle is that all radii, all distances from the center to any point on the circle are the same. And that means, right? Whoops, I tried to change to blue and I didn't quite get there. That means that QM, QN, and QP are all the same length because they are all radii of circle Q. Right? They're all radii of circle Q, so they all have to have the same length. Let's take a look at letter C. If point M was mapped to point P using a single clockwise rotation about point Q, through what angle should the rotation take place? All right, so if I want to rotate point M all the way over to point P, using as a center point Q, what angle should I use? Pause the video now. Well, you know, I need to use 125 plus 55, right? I need to rotate it that angle plus that angle. So it'll be 125 degrees plus 55 degrees, and that means I would have to rotate it 180 degrees. Awesome. Final piece, letter D. What does the answer to part C tell you about the points M, Q, and P? Well, see if you can write something down about this. Well, if this angle is 180 degrees, then that of course means that MQP is a straight angle, which means that points M, Q, and P are collinear, right? So anytime you rotate a point 180 degrees about another point, the original point, the center, and the image point are all collinear. They all have to lie in a straight line, otherwise it wouldn't be a 180 degree angle, right? If they didn't lie in a straight line, there'd be some kind of bend, right, in the angle, and the angle wouldn't be 180 degrees. That is a surprisingly important fact for us later on. All right, so let's wrap this up. Today, we saw the first formal look at a rigid body transformation, right? The rotation, all right? And the rotation is defined in a very specific way using a circle. So when I ask you to rotate a point about another point, right? Then you're simply going to sort of draw a point, or you're going to draw a circle, right? That has that center as its center point, and as a radius, you're going to have, you know, the length between the center point and the pre-image point. And then you're either going to move it clockwise or counterclockwise around that circle by a particular angle, right? And that angle is simply going to be defined as the angle between the original ray and the final ray between the center point and the image point, all right? Rotations are a little complicated, which is why we're going to do a couple days on them. This is only day 1. We'll get a lot more work with this in day 2. For now, I just want to thank you for joining me for another geometry lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.